Oh boy.
When I wake up each day, I feel so weary. Try to face the world, but it's so dreary. But I found that special thing that makes me cheery. Time to do music theory. Music theory. You're watching Adventures in Music Theory with your host, Dr. Robbins.
So, welcome to the Thursday, April 9th edition of Online 20th Century Idioms course. We just finished our unit on non-serial atonality, and we had a lovely test on Tuesday, and I'll be posting a video that goes through the answers to that test at some point so you all can see exactly how things were figured on that. But today we're going to start the next thing, which is serial atonality. And when we talk about non-serial atonality or free atonality, we're talking about that style of music that originates in the early 20th century, most notably with composers like Schoenberg, who are trying to find a way to write without a tonal center, but they don't have much of a system beyond what they're trying not to do. And what they're trying not to do is create tonal expectations, create that sense of a tonic being the main pitch that's supported by other pitches that happens in basically all the music in the centuries before the early 20th century. So, that stuff is hard to do, and there was a lot of looking for systems to make atonal composition more easily doable, and I'll talk a little about the history of that later on. But today I just want to hit the ground and talk about what we're talking about when we're talking about serialism. And what we're referring to is we're referring to that thing that's also referred to as 12-tone music, or sometimes people call it dodecaphonic music, which is, dodecaphonic means 12 tones. Dodeca is 12. Some people call it duodecaphonic music. But the thing that all of these have in common is that they are serial approaches to composition, which means they make use of a series. And that series is the important thing. Writing with a 12-tone or a dodecaphonic series is an important thing. So how does that work? Well, the way we get a series is often this. Composers do it by creating a series, or what's referred to as a tone row, which is a row of tones, a collection of notes that happen one after another. A lot of times it's a 12-tone row where all 12 chromatic pitches are there. As the system gets more refined, we're going to find there are going to be composers who realize they can work with a 7-note row or a 9-note row. But in the early days, all composers looked at was a way to take all 12 pitches and distribute them in a 12-tone row. And of course the thing is, if all 12 pitches show up once and only once in a row, it's hard for any one pitch to assert itself as the tonal center. So that gives them this use of having a system of music where there's no one pitch that asserts primacy like happens in tonal music. So, what are the basics of how this stuff works? Well, the basic is this. The 12 pitches are placed in a row. That row that a composer puts them in is called the prime form, the first form. And there's stuff that composers can do with that prime form, stuff that actually goes back to contrapuntal thinking and thinking that composers even had in the medieval era and stuff. Like, there was one thing you can do once you've got a bunch of notes in a row going one after another, is you can play them backward. And if you play the prime form backward, that's what we call the retrograde form. The other thing composers realize is if I have a row that goes like up a minor third and then comes down a minor second, I can take all my intervals and reverse their directions and make it go down a minor third and up a minor second. That's what's called the inversion of the row. And the other thing that can happen is once a composer has an inverted form of the row, he or she can play that backward as well. And that's what's referred to as the retrograde inversion. Pretty cool stuff, no? And look at the top of this little page here. We have one of those there tone row things I was talking about. If you look at what I've placed up there, you'll notice that all 12 chromatic pitches occur. And one thing that makes this different than non-serial atonality or free atonality is this. The order those pitches happen in is important. It's important that the B comes first and the G comes second and the D sharp comes third and the C natural comes fourth and on and on and on. That these pitches happen in a series. That's what makes it serialism. Now if I want to do some of those operations we talked about on the last slide, things like inversion, retrograde inversion, here's how it works. To create the inversion of that row, what I want to do to get the inversion is I want to take all of my intervals in the prime form and I want to reverse their direction. So the first interval in the prime form is a B natural up 8 half steps to G natural, up a minor 6 if you want to think about it in terms of tonal intervals. So in the inversion form, when I start on B, instead of going up 8 half steps, I think down 8 half steps to D sharp, down a minor 6. And by the way, here's something that's important. As long as I write D sharp for my second note, it counts as the inversion. Even if I don't really go down 8 half steps to get to D sharp. I could have gone up 4 half steps to get to the D sharp above that B, or I could have gone up an octave and 4 half steps to get to the D sharp that's like 2 ledger lines above the treble clef. As long as the second note's D sharp, it's okay. It's most easy to do inversion by thinking in terms of literal interval reversal. So for instance, when you go from the second to the third note of the prime form, it's a G down to a D sharp. That's a diminished fourth. So in the inversion form, since the second note's D sharp, instead of going down a diminished fourth, you want to go up a diminished fourth to G natural. And in the prime form, we go from the third note to the fourth note by going from D sharp down to C natural. So in the inversion form, since we went down 3 half steps in the prime form, we're going to go up 3 half steps in the inversion form. And we're on G, so we're going to go up 3 half steps to B flat. And that calls attention to something important as well. Notice when I went from the third to the fourth note in the prime form and I went down 3 half steps, it's written as an augmented second from D sharp to C natural. In the inversion form from the third to the fourth note, when we go up 3 half steps from G to B flat, I wrote it as a minor third. And I'm going to say something I would never say in tonal theory, and that's this. It doesn't matter how you write that interval, as long as it's got the right number of half steps in it. Augmented second and minor third are equivalent in this system because they both contain 3 half steps. So when I go from the fourth note to the fifth note in the prime form and I go from C down to A and I get a minor third, then in the inversion form and I'm on B flat, I go up 3 half steps and I go from B flat to C sharp. I could also have gone from B flat to D flat if I wanted, or for that matter I could even gone from B flat to E triple flat if I just wanted to make everybody really mad at me. But as long as the span of the interval is okay, it doesn't matter if you write the exact same interval. You don't have to replicate size and quality. You just have to replicate the interval span. I hope that makes sense. Getting the retrograde forms is really much easier. Once you have your prime form written out, the retrograde form is just the prime form backward. So since we get the prime form by playing those pitches from left to right across the page, what we do to get the retrograde form is we take those same pitches and we play them from right to left. So if the prime form starts out B, G, D sharp, the retrograde form is going to end D sharp, G, B. If the prime form ends G sharp, D, the retrograde form is going to start out D, G sharp. That's fairly user-friendly, as is the retrograde inversion form, because once you've got your inversion, instead of taking your inversion and going from left to right, you take your inversion and you go from right to left. So the inversion starts out B, D sharp, G. So the retrograde inversion ends in the reverse of that, G, D sharp, B. And since the inversion form ends F, D, G sharp, the retrograde inversion does that backwards, G sharp, D, F. That's fairly forgiving and easy to do, I hope. So that gives us 4 forms of a row. The prime form, which is going left to right, the retrograde form, which is going right to left, the inverted form, which is going upside down, and the retrograde inversion form, which is going upside down and backward. But there's a lot more that can happen. Like one thing that can happen with the prime form is you can just transpose it. And you can transpose it 12 times. And what I've got on the slide you're looking at now is I've got the prime form on the top, and then I've got the prime form transposed up a half step beneath it. And you can see that that does give me something different to work with. I've still got all 12 notes going on in both of those row forms, but now there's a different note in each place. One starts on B and goes up to G, one starts on C and goes up to A flat. And if I transpose it up another half step, I'd get a version that started on C sharp and went up to A. And I could do that, as I said, 12 times, and I'd have 12 unique forms of the prime row, which means I could also take my inverted row and transpose it 12 times, and I could take my retrograde rows and do that to them as well. And this could get oh so messy if I wrote all those down in notation. So what do we do? What we do is this. Since there are 12 possible prime forms and 12 possible inversion forms and 12 possible retrograde forms and 12 possible retrograde inversions, we need to find some way to get them all where they're easy to see, easier than writing them all out in notation. And that's where we come up with the matrix. A matrix is useful. Want to know why a matrix is useful? A matrix is useful because when you're using a matrix, it shows you all of the possible prime forms and all of the possible retrograde forms and all of the possible inversion forms and all of the possible retrograde inversion forms in a nice, easy grid. So what I've got here is I've got a blank 12-tone matrix, and I've got the prime row expressed in notation above it. And we're going to fill in that matrix. It looks like we're going to play Sudoku or something like that, but it's probably not really going to be that fun. But the matrix is sometimes also called a magic square or a Babbitt square, after this composer named Milton Babbitt, who was a 12-tone composer in the mid-20th century who did a lot to further how people thought about how to go about approaching 12-tone music. But anyway, what we do is this. In the matrix, we're going to fill in all of the rows and all of the columns with different forms of our prime row or our inversion row or our retrograde row or our retrograde inversion rows. And the easiest way to do it is this. Once you've got your prime row, you want to just write it across the very top row of the matrix. Like what you're seeing happen now. And if you look, you'll realize that every pitch that's in the staff up there has been put in a box. And then what we're going to do next is we're going to take that first column down starting on B, and we're going to write an inversion in it. So since the prime row in the box goes from B to G, you can think of that as up a minor sixth or down a major third. What we're going to do in our inversion row is we're going to go the other way. We're going to go up a major third or down a minor sixth from B, and we're going to get D sharp. And then we're going to fill in the whole inversion row by doing that. Right? The G went to D sharp, which is like going down a diminished fourth or down a major third. So the D sharp that's second in the inversion row went up a diminished fourth or up in harmonic major third to G. And you can see that just like when we were doing it in notation, we're just writing all of our intervals basically upside down. So we filled in 24 or 23 out of 144 boxes. We've got a lot of work to do. But there's a way you can do this. And the way to do it is this. Let's go ahead and figure out how we're going to fill out that second horizontal row. It starts on D sharp. And when we read it from left to right going across, we're going to want to see a transposed version of the prime form. So we want to know what would the prime row look like if it started on D sharp. Well, when the prime row starts on B, it goes to G. That's like going down a major third, right? So if a prime row starts on D sharp and the second note is supposed to be down a major third, that second note needs to be B. If I look from the second to the third note of the original row on the top line there, it's G down to D sharp, which is like going down a diminished fourth or down a major third. So since I've got B in my second note on the second row, I need to think, what's it like to go down a major third from B? It's when you go to G. And then when I look at the third to fourth note in the top line, that's D sharp down to C, that's down 3 half steps. So what's down 3 half steps from G? It's an E. The other way you can do it is this. You can realize that every note in the second row is a major third above the note above it in the first row. So you just look at the top row and write a note a major third underneath each thing. Since there's an A, we're going to write a C sharp. Since there's a B flat, we're going to write a D. Since there's an F sharp, we're going to write an A sharp or a B flat. You can think inharmonically all day long here. Since there's an E, we're going to think up a major third from that, or up 4 half steps from that to be more fair. And we're going to write A flat or G sharp. And when we think up 4 half steps from C sharp, we're going to write whatever's 4 half steps up. I've got F. If you wrote E sharp, that's fine. You're a little bit mean, but that's fine. What's 4 half steps above F? The easy answer is A. 4 half steps above G sharp is C. And 4 half steps above D is F sharp. Still with me? I suppose we'll know soon enough, because now we're ready to do the third row. And the third row starts on G. So one way to think about it is, since the second row started on D, how far is it from D up to G? The second row started on D sharp. Since the second row started on D sharp, how far is it up from D sharp to G? That's up 4 half steps, or up a major third. So I'm going to write a major third above every note above it in the second row. So what's a major third above B? It's a D sharp or an E flat. A major third above G is B. A major third above E is G sharp or A flat. Major third above C sharp is E sharp, or let's be nice and call it F. Major third above D is F sharp, and if you wrote G flat, that would be perfectly legit. 4 half steps above B flat is D. 4 half steps above G sharp is B sharp or C. 4 half steps above F is A. 4 half steps above A is C sharp and D flat and all variations of that. 4 half steps above C is E. And 4 half steps above F sharp is A sharp and B flat. And that gets us to our fourth row down, which starts on B flat. So we're going to rethink our interval here, because the third row started on G. If the fourth row starts on B flat, it's 3 half steps higher. So I'm going to write whatever's 3 half steps higher, or a minor third up, beneath the notes directly above them. So what's 3 half steps above D sharp? I like F sharp. 3 half steps above B is D. 3 half steps above G is B. 3 half steps above F is A flat or G sharp. 3 half steps above F sharp is A. 3 half steps above D is F. 3/2 steps above C is D sharp or E flat. And again, you could use either one. You just sort of do whatever seems convenient in the moment. 3/2 steps above A is C. 3/2 steps above C is E. 3/2 steps above E is G, or F double sharp, or A double flat, but don't you dare. And 3/2 steps above B flat is D flat or C sharp. Which brings us to our fifth row, which starts on C sharp. And the last row started on B flat, so how far is it from B flat to C sharp? It's still 3/2 steps. So we're going to write 3/2 steps beneath every note in the fourth row for the fifth row. So 3/2 steps above F sharp is A, 3/2 steps above D is F, 3/2 steps above B is D, 3/2 steps above G sharp is B, 3/2 steps above A is C, and 3/2 steps above F is G sharp or A flat. 3/2 steps above D sharp is F sharp or G flat. 3/2 steps above C is E flat or D sharp. 3/2 steps above E is G. 3/2 steps above G is A sharp or B flat. And 3/2 steps above C sharp is E. Like it goes. And we are going to fill in this whole matrix, but I'm going to try to find a way to make it a little less tedious and show you other ways you can do it, because the more ways you know to construct it, the more ways you can check your work. Right now we've been going left to right and making prime row forms, but we could also go top to bottom and make inversion row forms. In fact, if you look, we've already got 5 notes from one of our inversion row forms, the one that goes G, B, D sharp, F sharp, A, when we start coming down the second column. So we could do what we've been doing horizontally, vertically with our notes there, and we could just compare how far the notes are. Like when I look at column 1 to column 2, column 1 starts on B, and the note at the top of column 2 is G, so that's down 4/2 steps. So I could think about every single note in column 2 as being 4/2 steps below the note on the left of it in column 1, which means when I get down to that first blank in the second column where I see a C natural, I can figure out, so what's 4/2 steps below C natural? And that's going to be A flat or G sharp. And 4/2 steps below E natural is C, and 4/2 steps below F sharp is D, and 4/2 steps below A is F, and 4/2 steps below F natural is D flat or C sharp, and 4/2 steps below D natural is B flat or A sharp, and 4/2 steps below that G sharp on the bottom is E. So now we could try our third column, and since the second column top note to the third column top note is G to D sharp, that's down 4/2 steps. And if I look at what's filled in there, I realize, well, everything's down 4/2 steps. So when I go down to my first blank box there, there's G sharp to the left of it in the second column, so I want to go down 4/2 steps, which means I want to write an E. And then I want to write whatever's 4/2 steps below C natural, which is A flat or G sharp. What's 4/2 steps below D natural? That's A sharp or B flat. 4/2 steps below F natural is C sharp or D flat. 4/2 steps below D flat is A. That's the easiest way to express that. 4/2 steps below B flat could be G flat or F sharp. And 4/2 steps below E is C. And once you've gone through and done all of this, you'll get a matrix where there's a letter in every single box, and it will look like that. Hooray! Don't we all feel good about ourselves? It may be that once you look at that, you realize this is a little confusing because of enharmonics. Sometimes my matrix might have D flat, sometimes it might have C sharp, sometimes it might have G flat, sometimes it might have F sharp. So it can get a little bit confusing. And whenever we're doing a matrix that uses the letter names, we're creating what we call a pitch class matrix, because letter names are pitch classes. There is another way to do it, though. Look at this one. It's just got numbers. And when you use numbers, you're creating what's referred to as an integer matrix. And with an integer matrix, the way this one in front of you right now is constructed is I took the first note, which is B, and I called it 0, and then I measured how far was it from 0 to the second note. Well, when I went from B up to G, that's up 8 half steps. And then I measure every note by how far away it is from the first note. How far is that D sharp from the initial B? It's up 4 half steps. How far is that C natural from the initial B? It's up 1 half step. That A is up 10 half steps. Always measure up when you're doing this. You don't want to get the same number twice, and you don't want to deal with negative numbers. So when we measure from the B up to the high B flat there, that's up 11 half steps. And from that B natural up to the F sharp is up 7 half steps. And if you do it right, then in the top row of your integer matrix, you'll have every number from 0 through 11 one time and only one time. And when you look at any row or any column in the matrix, you'll realize that any row or any column has every number from 0 through 11 once and only once. And here's an integer matrix, but it's a little different. Now instead of starting out going 0, 8, it starts out going 11, 7. And the reason it's doing that is because instead of thinking about B, which is the first note in my prime form, as being the 0 note, I'm thinking in terms of fixed 0 numbers. Remember those? And I'm saying, well, B is 11, always and forever. And C is 0, always and forever. And C sharp is 1, always and forever. And I'm setting it up that way so that when I do this, I'm giving every pitch in the prime row its fixed 0 name. Here's our first integer matrix again, the one that called B0. That's a fixed 0 integer matrix. And when we're dealing with a fixed 0 integer matrix, that means C natural is always going to be 0. And C sharp is always 1, and D is always 2, and B flat is always 10, and B natural is always 11. So I can know a little bit more information from the numbers with a fixed 0 integer matrix. Like for instance, if I look at this matrix and I look at the very bottom row and I look at the second to last note, since it's a 5, I know that that's an F because 5 is always F in fixed 0. There is no right or wrong in terms of fixed 0 versus movable 0, or even pitch class matrix versus integer matrix. All three of those types are used. I find myself favoring the fixed 0 integer matrices, but I'll probably have you all try to do all of those. And I'm going to show you how to go about actually labeling the row forms on a matrix next. So get ready for excitement. The way we do not order rows is just by going in order 1, 2, 3, 4, 5, 6, 7 through 12. Instead, we order rows based on which pitch they are organized around and what number that pitch is. So what you're looking at right now is the movable 0 integer matrix. And what it's showing us is how to read all the rows from left to right, all the prime forms, which we call P forms. And the prime form that starts the top row starts on 0, so we call that row P0. The prime form that starts on the pitch 0 in movable 0 parlance. And the next row that starts 4 half steps higher is called P4. And the third row down that starts 8 half steps higher is called P8. And again, this is because we're using movable 0. Some people, instead of calling it prime forms, they call it P forms for prime, but some people call them T forms for transpositions. So just be aware if you ever see a 12-tone analysis that talks about T8 or T2 don't be freaked out. That's what we would be calling P8 or P2. But both are used. I think I prefer prime forms, and I think that given all we're dealing with this term, that's going to be the only one I expect you to be accountable for. So let's continue using this movable zero integer matrix, and if you look across the top at the red letters, you can see that those are numbering our inversion forms. And it's the same way we number our P forms. The pitch which is first is the pitch that gives it its number. So if you play the inversion form that starts on the 0 pitch, which is B for this particular incarnation, you call that I0. If you play the one that starts 8 half steps higher, we're going to call it I8. If you play the one that starts 4 half steps higher, we're going to call it I4. So P forms and I forms both use the letter P or the letter I followed by the number that represents the first pitch in the row, the row that it starts on. And most people find that to be fairly clear, which is good because I'm about to make it muddy because now we're going to talk about retrograde forms, which is what happens when you read the matrix from right to left, like that arrow that just showed up is showing us. And there are the numbers for our retrograde forms. They may not be what you'd think. You might be looking at that top one and be trying to figure out why are we calling it R0 when the first note I would play when I was doing it is 3. Why am I calling it R4 when the first note I would play would be 7? Here's why. Look at what the last note would be if you played it. R0 there, yes, if we played it, we would go 3, 9, 6, 2, 5, 7, etc. And when we finished, we would end on the pitch 0. And for retrograde rows, they get their number by what pitch they end on. So since that pitch ends on pitch 0, we call it R0. And the reason why is because what that's really saying is it's just the retrograde form of P0. So the next pitch down, the next row down is R4 because it ends on pitch 4, which is of course the pitch that P4 starts on. And the retrograde inversion forms that go from the bottom up are the exact same deal. Yeah. The very first retrograde inversion form I'm looking at there that goes from the bottom to the top and starts on 9, it ends on 0, so I'm going to call it RI0. The next one I'm going to call RI8 because it's the retrograde inversion that ends on pitch 8 when you perform it. It's the retrograde inversion of inversion 8. So P forms and I forms take their number from the pitch they begin on. R forms and RI forms take their number from the pitch they end on when you perform them. Okay, and here's how things would work with a fixed 0 integer matrix. Since we're using fixed 0, that top row doesn't start on 0 anymore. Since it began on B and we're in fixed 0, it's actually starting on pitch 11. And we would call it P11 if we played it from left to right. And if we started on the inversion form that starts on B, that goes from top to bottom in that first column, we would call it I11. And if I played that top row that was P11 backwards from right to left, I would call it R11 because it ends on the pitch 11. And if I played that first column from bottom to top, when I go from top to bottom, it's I11. So when I play it from bottom to top and it ends on B, I'm going to call it RI11. And that's how fixed integer matrix would work with this. So the process for getting the numbers is basically the same. To get your P forms, they take their number from whatever that note in the leftmost box is. To get your I forms, they take their number from whatever that number in the topmost box is. And then the R forms, you give them their number from what pitch they end on when you perform them. And for the RI forms, you give them their number from what pitch they end on when you perform them also. I think I said that sensibly. Hang on, I'm going to show you something neat to help you check your work and see if you've gotten your matrix right when you construct it. Here's that fixed zero integer matrix we were just looking at. And if you'll notice, I've taken all the numbers that start diagonally in the upper left-hand corner and go diagonally to the lower right-hand corner, and I've turned them red. And I'm hoping that by making them red, you'll notice the interesting thing about that diagonal descending left to right slash, which is it's the same number all the way down. It's pitch 11, or if you want to think about what note it would actually be, it's B natural, all the way down from the upper left-hand corner to the lower right-hand corner. That's not a special property of this matrix. That's how every single matrix out there will be. Here's what it would look like with a movable zero integer matrix. Again, notice if you look in the upper left-hand corner, we see 0. And if you follow that diagonal line descending to the lower right-hand corner, it's all zeros. And they're easily marked in red on this slide so you can see them. And of course, just to remind ourselves, if we look at the red numbers on the top and on the left side of the thing, that'll show us how we go about numbering our P forms and their I forms. And let's look at a pitch class matrix where we use letter names instead. And you can see that that property I talked about a minute ago with the diagonal line being the same thing is evident here too. There's B in the upper left-hand corner, and then there's a diagonal line of B's that go all the way down to the lower right-hand corner. So you're going to see that in every matrix, regardless of whether you use integers or pitch classes. The one thing about pitch classes, though, is this. Because of enharmonics, it may not always be as apparent. There's a chance that if you were like doing a pitch class matrix, if your note in the upper left-hand corner was F sharp, you could, for some weird reason, see a G flat show up here and there. And that could look like it wasn't the same thing. So this is actually one reason why I preferred using integers for matrices, is because there aren't enharmonic versions of the numbers we use. So you'll always see the same character showing up from the upper left to the lower right. Here's how that can be helpful when you go to build a matrix. If you're going to build a matrix and you know that it starts on B in the upper left-hand corner, then why not just go ahead and write a whole big diagonal line of B's descending from the upper left-hand corner to the lower right-hand corner? Now, why would you want to do that? Well, one reason is it's mindless and it's fun to do. But the second reason is this. If you go ahead and you fill in that diagonal because you know it's going to be the same pitch all the way down, then as you go to put in your other row forms, your inversion forms or your prime forms or whatever, those B's that you've already put in can help you. Because if you're writing across there and you come to a square that has a B in it and you don't think it should be a B natural in that square, that means you've slipped off somewhere on the way to that note, because that should definitely be a B natural going down on diagonals in this particular matrix. Likewise, if you're working on these and there's like a B natural, say, in like the 8th spot on this, when you get there and it's supposed to be B natural, you'll feel good about yourself, and it'll let you know you've been constructing your row form correctly up to that point. So it's sort of a good way to check your work. And speaking of work, here's a song we can analyze for next time. I'm posting it on Moodle and on Google Classroom. This is the first song from a collection of 3 songs by Anton Webern for voice and piano. And one thing you might want to do is actually go listen to it. I'm sure there are plenty of performances of it floating around on the internet. I think I told you all that one student who took this class a few years ago got so crazy that she actually did these on her recital at Converse and stuff, because that's what happens when the 12-tone bug bites you. So let's talk about the assignments I want you to do after you've treated yourself to a nice listening of this song. I want you to build a PC matrix for this song using letter names. So I want you to look at the song and actually figure out what would be the matrix, which means you need to go through and find a row. I'm giving you this song because it's one of the easier ones to get a row out of. I would say use the vocal part and look and see if there's anything going on in the vocal part where you have all 12 chromatic pitches being done in succession. If so, that's your row. And if it's the first one you find in the song, you can write it across the top of your matrix. Yeah, if we were actually meeting in the classroom, I would be physically handing you all graph sheets that have like matrix squares on it, but you're going to have to fend for yourselves on that. I think you can do this. But I want you to build a pitch class matrix, the one where you use letter names, where you say E and where you say B flat and F sharp and stuff like that. And I'm going to want you to hand it in to me so I can look at it and grade it. It's not going to be fun to grade, by the way, but I feel like it's something I should do. Okay, then after you've made a pitch class matrix using letter names, go construct a number matrix, a fixed zero integer matrix. So if it's fixed 0, that means you're going to call C natural 0 all the time. You're going to call C sharp and D flat 1 all the time. You're going to call D natural 2 all the time, etc. I'm also going to ask you to hand that in because I don't have enough tedious stuff to grade. And then after you've constructed your fixed 0 integer matrix, can you see this coming? Construct a movable 0 integer matrix, which means regardless of what note the first row starts on, you're going to call it 0. So if the first row starts on F sharp, don't do what you do in a fixed 0 matrix and call it 6. Call it 0. So basically you're just going to do some fancy math to the fixed 0 integer matrix you just made. But construct a movable 0 integer matrix. Hand that in to me as well so I can go crazy. These things are going to be tedious to grade, but grade them I shall. So understand there's somebody sharing your pain. Okay, after you've done that, on the piece, on the matrices you give me, label the row forms. Tell me the top one is P0 or P6 or whatever. Label the P forms, the I forms, the R forms, the RI forms, so that I know you're doing that right as well. And then what you don't turn in is look at the score again, and on the score, label the row forms Webern is using at different points. It's easy to do with the vocal part because the singer can only sing one note at a time. The piano part's going to be a little bit more annoying because they can do things like play more than one note at a time in a chord. And if you do that, it's hard to tell which note comes first. It sort of messes up with the idea of series because it's simultaneous. So you have to sort of untangle and guess. But on the score, look and see which row forms you think Webern is using from moment to moment to moment. And on Tuesday's video, we're going to actually go through and discuss that. So make sure you've done it in advance. And I'm going to be posting a second video after this one, which is also available immediately, so that you can have even more experience building a matrix, and so that you can have a little bit more of the background history on how serialism came to be. Okay, and I think we're done with this part of our video. So, take a few moments to decompress and think about all this. And then if you want to, there is another video available, which is called April9 20th Century Part 2, that'll take you through yet another matrix construction if you think that would be useful. It'll also show you some cool shortcuts for how to get your inversion forms on your row a little bit faster. So have fun with that, and I will see you in the next video. Enjoy.